All right, hi, my name's Chris Jones. I'm the flight software cognizant engineer for the Psyche project at NASA JPL. And I'm going to talk about our use of time and space partitioning in our flight software. In case you haven't heard about the Psyche mission, it is a spacecraft going to an asteroid in the asteroid belt, also called Psyche, that's believed to be made of mostly metal and possibly a protoplanet core. So before I get into what we did on Psyche, though, I'd like to talk a little bit about the legacy flight software that we've used at JPL on several of our past large-scale missions. So this software really started its life with Mars Pathfinder back in 1996, and then that was inherited for the Mars exploration rovers. Then it went through a period of, you can say, institutional refinement and expansion with a task called MSAP. That became the Mars Science Laboratory flight software, and then the SMAP and Mars 2020 missions inherited Mars Science Laboratory. So in every case, this software is embedded C code, and it executes on a radiation-hardened PowerPC processor. At a little bit lower level of detail, the legacy flight software at JPL really has the following properties. So first of all, it's module-based, meaning its functionality is decomposed into independent modules. This architecture is multi-threaded, where as a general rule, each module has its own thread of execution. There are exceptions, but that's generally the case. It is a priority preemptive architecture, meaning that if a higher priority module needs to perform work, it's going to take the CPU from a lower priority module and then give it back when it's done. This architecture also, the hardware communicates with the software by raising interrupts, so it's hardware interruptible. And this is a system we can largely think of as event-driven, right? So we have modules. Modules are threads. They depend on message queues. The message queues wake up when they receive a message and they do work. Messages that are received are going to be from other modules, from an interrupt or a timer expiring, some kind of system timer. And we can say that this is a partially deadline enforced architecture, meaning that there's a few threads that have like the highest priority. They have to complete their work every control cycle. But the rest of the threads, they run opportunistically and they don't have any real deadlines, and the work is essentially unbounded, or the time to complete the work is unbounded. So, like I said, we've used this architecture several times in the past, and we have a pretty good handle on what its pros and cons are. So on the pro side, right, it's pretty simple as far as implementing it in a flight software module. Each module is just a series of event handlers and a wait loop that waits on messages. It's also very efficient. We can use 100% of our CPU as long as those few deadline-enforced threads get their work done, right? Can be fully CPU efficient. We have an established flight history, so this architecture has landed on Mars more than once. And it's really become part of our engineering culture at JPL. It's not just that the flight software team understands how it works. It's like our operations team understands it, or our systems engineers. It's really, at JPL, when you have conversations about how flight software works, it's generally this architecture. That being said, though, the architecture isn't without its drawbacks. So the first of those is all the modules execute in a big shared memory space, meaning that one module is going to be able to corrupt the memory space of another module. Also, there's really no concept of kernel space versus user space. Everything runs in supervisor mode, so a misbehaving module could corrupt operating system data structures, execute some kind of privileged instruction. Also, the executable that is built with this flight software, it's a single monolithic executable, meaning that if we want to update the flight software in flight, we're going to need to upload the entire executable again. And that's like 20 to 30 megabytes, and at low downlink rates, that's a significant operational impact. So also this architecture has issues with scalability, right? Because if you add a module that has a higher priority, all of the modules with lower priorities, their execution timing and characteristics are going to change because what you just introduced is going to start stealing CPU time. And in the worst case, you're going to have a situation where a module could be starved and not get to CPU at all. Also, this, as I said, is a multi-threaded architecture, and it's a multi-threaded architecture that shares data between modules. So whenever you have a system like that, you have to have things like locks or semaphores, mutexes, that make sure that there's, the data is shared in a coherent way. That's not unique to this system, it just comes with the territory. Finally, this system, I would say, software is not really in the driver's seat. It's just reacting to external events. And usually those external events come in the form of interrupts, right? So software doesn't determine when it does things all the time. It's reacting to external stimuli. And that makes the behavior of the system difficult to model, especially in stress cases. And you can have like emergent behaviors, emergent interactions between modules that become difficult to predict. So all of these cons that I mentioned, right, these grow as flight software grows in scale and grows in complexity. So to address these drawbacks, JPL started working on a next generation flight software architecture for our large scale missions. Started back in 2013, and it leverages a technology called time and space partitioning. I'm sure a lot of us here are familiar with that. But that was used in the aircraft industry starting in around the 1990s, and it allows you to take computers that were spread across the system, so small computers for multiple functions, sort of a federated system, and consolidate that into a single avionics box called an integrated modular avionics. So this has a lot of benefits, reduces size, weight, and power. There's less things to build, less things to maintain, less things to test. At a software level, what we're really doing is we're allowing safety-critical software and non-safety critical software to be co-resident on the same computer. And we do that by breaking the software functionality into units, we call them partitions, and we can really think of them being firewalled off from each other. They're firewalled off in what we call the space dimension, meaning memory, and the time dimension, meaning when is it going to execute on the processor. So just getting into a little bit more detail about space partitioning, the way this is done is we use the real-time operating system to program the memory management unit on the flight computer to give each partition its own memory space and then prevent other partitions from interfering with it. So looking at this example, you can see here we have 3 partitions and we have memory space. You can see partition 1 accesses its own memory. That's fine. Partition 2 also accesses its own memory. That's a legal access. But partition 3 tries to access partition 2's memory space. The MMU catches that. That is an illegal access. And in time and space partitioning parlance, that's called a space partitioning fault. So similarly, time partitioning is, again, when we use our RTOS, but here it's to make sure that each partition gets its own time to run, its own time slice or partition window. And those partition windows, they execute on a repeating schedule called a major frame, and that major frame is broken into smaller, equally sized segments called minor frames. And then within the minor frames, we have arrangements of partition windows. You can see in this example, we have a 1 hertz major frame, a 16 hertz minor frame, and then in each minor frame, we can have different arrangements of these partition windows, which are these blocks that have the letter P on them. So if a partition fails to complete its work in its allocated time, it is said to have committed a time partitioning fault. Okay, so we took on Psyche, we took these time and space partitioning principles, and we used it to construct a software architecture that addresses the cons in our legacy software system. And we did it by implementing really the following architectural properties. So on Psyche, we're not module-based. Now we consider ourselves partition-based. So functionality is still decomposed into modules, but those modules are grouped into partitions in an informed way. So we do that based on functional cohesion, right? So modules that are inside of a partition should generally have the same, function or own the same functional domain. We should minimize the data flow between partitions. So we want any kind of tightly coupled data flow to be within partition boundaries. We want to be able to isolate hardware faults, and we want to segregate safety critical functionality from non-safety critical functionality. So for example, we would want to put all of our science instrument management in a non-safety critical partition and our G&C device management and algorithms in a safety critical partition. So the biggest difference between, I would say, this architecture and the legacy system, though, is we are single-threaded. All of our modules execute sequentially on a single thread, and every partition is deadline enforced. So every partition has to complete its work every control cycle. Also, interrupts are disabled. We are a polling-based architecture. So the software controls when we talk to hardware, when hardware can tell us something. We also leverage our MMU so that partitions cannot corrupt each other's memory space. And we have a concept of dual mode execution, meaning that most of the flight software runs in user mode, and we have a small amount of support code running in kernel mode. Okay, so as I said, we were able to eliminate those legacy architecture challenges, but we also encountered some new challenges in the form of what I would call execution time variability. So remember that to avoid a time partitioning fault, we have to make sure that a partition will never exceed its deadline under any circumstances. So that means we have to size those partition windows based on the absolute worst case scenario. So, looking at this example right here, this is the start of a partition window. Over here's the deadline. We have a minimum case, so that would be like when the system is completely quiescent. Average case, this would be like when we're doing normal flight operations type activities, command processing, for example. And then the worst case would be like some stress scenario or like some pathological situation where the hardware is throwing inputs at us. And this difference between the minimum time and the worst case time, that's our execution time variability. And if we don't minimize that and carefully manage it, we end up with a situation where all of our CPU bandwidth is basically eaten up by trying to deal with the worst case. So therefore, characterizing and minimizing that delta really became the bedrock of our development culture. That was kind of the technical challenge we were always wrangling. So we implemented this architecture. Spacecraft is actually flying now. We're doing our first software update. And we were able to see what are the pros and cons of this system we created. And I would say one really overwhelming pro, is that it is easy to reason about the behavior of our system. We're able to exactly predict the ordering of system events. When is a module going to run? When is data going to propagate? When are we going to produce telemetry? When are we going to dispatch commands? So these are all things that we have a really clear understanding of. So that clear understanding also allowed me as a software lead to be able to interact with our systems engineering group. And they would ask me questions like, we need to add this functionality, we need to change this requirement. And that often ended up being, okay, we need to add a module, or we need to add commands. And because our system was so deterministic in how it was structured, I could provide those impacts pretty quickly, both in developer time, software scope, risk. I'd also say our anomaly investigations. As we were developing the software, of course, some small amount of bugs were found. And the bugs that were found didn't require deep analysis by our development team. So we didn't have a situation where we had a developer pouring through a log of like, we had this many thousand context switches, all these different threads, this message goes here. We didn't have to worry about, is this task being starved? Is the data incoherent? Oh, this strange ordering of events occurred. So we didn't have to worry about any of that. And honestly, our developers were able to get to the bottom of most software problems within, a matter of hours. So also, we had to decompose the software into partitions, and we had to plan the execution schedule very early in development, just to be able to build everything out. And that really caused us to front load our design early in the project. And that made the design very stable. We had a really firm understanding early on of what the system looked like. So we didn't have very much churn. And actually the execution schedule that we had at PDR looked very much like the execution schedule structure that we launched with. So also space partitioning, if a developer was having a problem with trying to use memory that was belonging to someone else, that was caught very early. It didn't make it into some kind of latent problem that we would encounter in flight, right? The MMU bit us immediately. On the negative side, again, I bring up this execution time variability. That was pretty challenging for our software team because it's not something that a lot of developers think about. And they think, I'm going to do a mem copy that's a few kilobytes. They just say, do the mem copy. But here you've got to break the mem copy up, and do a few kilobytes every control cycle so that you're not doing a burst of activity in the CPU. So that really, that difficulty led the leadership of the team and peer reviewers and test engineers to really be very observant and very careful about unbounded computation. So that's something that came up a lot during our code reviews. So also just really by nature, right? Time partitioning is not quite as efficient user of CPU resources as the legacy system. So, for example, everything is deadline enforced in our system. And to meet our institutional design principles, we had to leave 20% of the CPU margin unused at launch. The way that this, slight decrease in efficiency really manifested is in the legacy system, we could generate a telemetry packet once every second. And in this system, we had to drop that down to generating telemetry packet once every 5 seconds. That was something that, the project was able to deal with. It's not that big of an issue, but it was a decrease in capability. And also, this may sound like a pro, which is space partitioning is inherently secure. But if you have a tool set that likes to be able to peek and poke memory anywhere in the system, those space partitioning boundaries can become onerous, right? So it could affect testing. Okay, so now that we've completed this development on this new architecture, what are our lessons learned? So I think having some kind of software framework that manages its execution time variability would be tremendously helpful. Maybe it would break up mem copies or bound loops or break behaviors into linear state machines for us. Or if we could give that framework an execution time budget for every module that allowed us to help keep track of that, it would have helped our development team make this transition. Also, we had some cases where we would try to inherit modules from the legacy system and bring it into this deadline-enforced time and space partition world. And we found that's generally not a cost-effective thing to do. It's basically, you need to cost that as a new development because you have to take all the computation that those legacy modules do and break it into discrete work steps. So, and you have to look for any off-nominal path that could lead to a burst in computation, and you have to address that. So what you're really doing is, you're fundamentally changing the design assumptions of the heritage code, which is why it kind of turns into a new development. So also this, changing this paradigm also really changes the way that we interact with our hardware, right? So if you're designing hardware that raises interrupts and software always responds to those interrupts, then the hardware can pass that state to the software and be done with it, right? But in a polling-based system, it's software that controls when it checks for events. And more than one event can happen in between polling intervals. So now the hardware needs to remember more than one event, right? So that means you might need more buffering, more registers, different FPGA logic. There were, in the legacy architecture, a lot of hardware-software interaction models where the software would give the hardware a little bit of work to do, the hardware would raise an interrupt, and it was sort of this tight loop of interaction. And in a polling model where we poll less frequently, that really needs to become what I would call a work list consignment model, where the software is going to build a list of things for the hardware to do, give that to the hardware would click through those operations, build a log list of results, and then have that ready when the software polled again. So again, that requires a little more hardware complexity. Also, we found, at least in our flight computer, DMA was not our friend. DMA caused execution time variability. So if we, in the flight software, tried to access the flight computer's memory at the same time DMA was accessing it, our flight software memory access was delayed. And in a system where you think about average versus worst case execution time, that's not a good thing. So you either need to eliminate the use of DMA or control when it happens. And we did the latter, right? So we were able to control when the DMAs occurred and that they didn't occur when we were doing the rate-based execution. Also, this is very specific to our case where we had, there's a spacecraft clock, spacecraft time source, and then there's a different time source that we use to drive our execution schedule. And we had to keep those things synchronized to maintain our spacecraft control cycle. That was a very difficult thing to do. If you can build a system like this using one time source, I highly recommend it. A little bit more at the institutional level, if you're going to make a big change in the flight software, it doesn't have to be time and space partitioning, but any big change, it might be obvious, but that has ripple effects across the project. It doesn't stay in the realm of flight software. And the institution and the project needs to be on board with this, the cost of this being a long-term development strategy to improve, how we do things. And, you might get the question, was this bug, was this weird behavior because of this new architecture? So I was asked that, more than once. Also, as I said, the scope here is beyond the flight software team. There might be systems engineers, people that write documents, people that write tests that really have the old architecture internalized and may need some training to understand how the new architecture works so that we don't, for example, write, onerous requirements or ask for things like a test that generates 10 times the data rates. That's going to be something for this architecture that's hard to manage. Okay, so performance. How did we do? So we launched in October. The flight software has been running until now. And we were able to successfully support launch, deployment, and initial checkout activities without any major issue. And this is a plot of the execution margin in each of our partitions. So you can see a couple of things. One, we have a lot of margin, right? We have like 30% margin or more in every partition. And for the past few months, these watermarks have been very, very stable, meaning that we really don't have a risk of a time partition fault. So we were able to manage that execution time variability and have enough margin. All right, so what do we want to do in the future? We did split our partitions into safety critical and non-safety critical, but the consequences of a fault in each are the same, which is a flight computer reset. In an ideal world, we would want the non-safety critical partitions to not reset us. We would want to be able to recover and not affect the safety critical functionality. Also, we have space partitioning in our flight computer memory, but we didn't extend it to the rest of our avionics hardware. So if one partition is using a particular hardware function, the other partition could interfere with it. We know how to extend it. It's something we plan to do, but it's just kind of fell off the plate, in the run-up to launch. Also, I think this architecture could be used to facilitate ITAR and EAR safe collaboration, because each partition is built as its own binary. So if one institution develops one partition and another institution develops another, you could just deliver the binary and then a series of APIs. So you don't have to exchange source code, which makes these, restrictions a lot easier to manage. And finally, I talked about that framework to manage execution time variability. We would like to, make some progress on that. So in conclusion, on Psyche, we leverage time and space partitioning. We use that to address the drawbacks in our legacy software. This transition, it did come with concerns, right? We have to deal with execution time variability, and we also are a little bit less efficient in how we use the CPU. We can definitely manage the former with developer training and software frameworks. And, the processor we used was pretty old. Processors are only getting faster, they're only getting more capable. So if we were able to do it on the processor we had, I think that problem is only going to get more manageable moving forward. So we successfully supported launch deployment and initial checkout. We have stable and healthy execution margins. And I think this architecture, because it is deterministic and it can scale, it's going to make an ideal candidate for further reuse and refinement.
We are over time, but there are so many good questions online. We go in person first, and then we have time for 2 questions online.
Okay.
Did it die? We might need a new battery.
Operator error.
Sorry, it looked to me like you wrote your own time-space partitioning scheme for this, and I was wondering, did you look, there are like A-Ring 653 OSs out there that do this maybe for you. Did you look at that?
So we didn't really completely write it ourselves, so it's based on Green Hill's integrity. There are some institution-specific modifications, but we use their partition scheduler.
Okay.
We did look into like the A-Rank, fully A-Rank-based OS. A decision was made early on because the way to do things in that architecture was pretty restrictive. I wanted to leave sort of the freedom to possibly change the architecture. One of the capabilities that we have that the A-Rank made difficult was being able to load partitions dynamically and run them. That being said, I would say, looking back on it, hindsight being 2020, I really think we should explore the A-Rank-based, software products a little more, especially what those Apex APIs could give us for free.
Okay, thanks. And sorry to take up one more. I was just wondering if you overall, if you go to a time-space partitioning, I think you risk high data coupling between the partitions such that it defeats the purpose. And I'm wondering if you ran into that, or you were able to really isolate your partitions so there wasn't that much data flow between them.
Short answer is I would say we were. I would say we did a lot of work early on trying to figure out what those partition boundaries would be. And that really didn't end up being too much of an issue.
Thank you, first of all, for your presentation. How much do you think that this transition of architecture, it was, let me call it easy, but just to understand, because you have so much heritage from the previous flight software, and instead how much it would be easier or difficult to do from scratch for new flight software?
I don't really think we gained that much by taking heritage. So like I said, JPL had an institutional product that had a lot of the time and space infrastructure. Taking that was obviously tremendously helpful, but like a module that was written in the legacy architecture that we brought over basically ended up being a new development. Sorry for taking so much time.
We have time for one online question, and when we can take it, we are running over. So online from Brandon, APL, for time partitioning CPU utilization, how did you calculate your CPU margins? That's first part. Second part, was it based on the partition allocation, or did you take credit for average or worst case execution time versus the partition time boundary?
So we had a framework that we wrote in the software that would give us high resolution measurements. So we tracked average case for every module, and worst case for every module and partition. And then we looked at the margin by what is the amount of time total that we have in the partition window, and then what percentage of it did we use in our absolute worst case. And so we had this high rate telemetry, and we asked people that ran in our test bed to downlink that data every time they ran. So we had thousands and thousands of runs where we had those statistics that we could look at.
Thank you, Chris. There are more questions online. Please follow up with them on Slack.
Okay.
Unfortunately, we are running out of time.
Yeah, I apologize for that.
Thank you so much.